Here is a function, something that we can plot an autograph for the volume of a cylinder. Volume is pi r squared L. Interesting how the volume changes with the length. So we plot the length on the x-axis, which is the independent variable, against the dependent variable, which is the volume on the y-axis, and keep all other variables constant. So 3 variables here: volume, radius, and length. We change the length, observe the volume, and keep the radius constant. And then we can put that onto autograph. Here it is, and see we get a straight line. So generally, we change or we control one variable. That would be what goes on the x-axis, and observe another, which is what goes on the y-axis, and keep the remaining variables constant. Notice we could have more than one. We could have 3, 4, 5 variables in a function, but we only ever change one and observe another. So the controlling variable is called the independent variable, and the observed variable is called the dependent variable. Which axis does the independent variable go on? Unlucky, x. Okay, x-axis. The thing that you're changing goes along the x-axis, and time is often the one, because we're looking at what happens as time goes by. So what's happened to something after 5 seconds, 10 seconds, or so on. And so time generally goes on the x-axis, and any other variable on the y-axis. So therefore the observed variable must go on the y-axis. Okay. So the same formula. How does the volume change with the radius? There are 3 variables. How does the volume change with the radius? So which is going to be the independent variable that goes on the x-axis, if we're interested in how the volume changes with the radius? The radius. So that will go on the x-axis. Volume on the y-axis, and length will stay the same, will be a constant. So in other words, if I wanted to plot this on autograph, what would I key into autograph? Or L, any less you want. Yeah, let's keep it as L for length, but that doesn't matter. The key thing is y and x. So now if I plot this on autograph, so let's go back to autograph, just change this equation to y equals pi x squared L. So now I'm changing the r to an x, and I'm changing the x to an L. Then hit OK. Now the graph changes. No longer is it a linear, because the radius is squared, so we weren't hopefully expecting a straight line. Perhaps I should have asked you that before I actually clicked OK. But you get, because it's x squared, you might recognize this curve as the quadratic curve. Okay? Again, we're only interested in the positive values for the radius, not when the radius goes negative. So this quadrant is all we're interested in. And again, if we're interested in how the volume varies over a radius of 0 to, say, 3 or 4 meters, then I would need to zoom out on the y-axis to get that in. So let's zoom out on the y-axis, zoom out on the y-axis, and then we get it to come down a bit. So we can see what happens. I'll have to go once more. Did it go the wrong way? Yeah. So it's just, again, familiarization with autograph and playing around with it. Now I can see how the radius changes over a region of 4 meters. So if I was only interested in that particular part of the graph, I could zoom in that part. There it is. And if I wanted to see, well, what actually is the volume when the radius is, say, 1.5, then I can zoom box in on the 1.5 bit, which is just here. And I can read off what the radius is when the volume is 1.5. Okay? So what about how does the length vary with radius? How does the length vary with radius? So this time, what's the independent variable going to be? Right, again, radius is the independent variable. How does the length change with radius? In other words, what happens to the length if I change the radius? So the radius is going to be the thing I'm controlling on the x-axis. So what's y going to be? Right, and this time the volume will be a constant. So what am I going to key on into autograph now? No? Because the volume is constant. So volume equals right, pi x squared y. Okay? I could rearrange this to read y equals volume divided by pi x squared, but as far as autograph's concerned, it only really needs to know which is the independent variable I'm putting on the x-axis and which is the one I'm putting on the y-axis. So I could type that in. So let's try it and see what happens. So let's change this equation again to read v equals pi x squared y. And hope it works. V equals pi x squared. And remember, if I want to put x squared in, I can use the little squared button, or I could just hit the x button twice, and it will give me x squared y. Hit OK and see what happens. So let's zoom out and see if we've got the function anywhere. Bring it into the middle, the axes for now. And here we go. Okay. Now let's zoom out on this function and have a look at it. And label it. Okay. Remember, if we look back at this, x is the radius, L is the length, and we're having a fixed volume. So x is the radius, and length is on the y-axis. Look at this graph. Fixed volume. Why has it got the shape it has? The volume is fixed at, say, 3 cubic meters. So what's happening to this graph? Why does it have this shape? Yeah. Yeah, exactly right. To keep the same volume, as I reduce the radius, the length's got to get bigger and bigger and bigger. Will it ever reach the y-axis? Because? Yeah, it can be infinite because? Yeah. Yes, that's the point, isn't it? If I cut the y-axis, it's because r has dropped to 0. And if r is 0, that really is not going to happen in the real world, is it? So this point often happens if we're trying to use a function and model something in the real world, like an engineering scenario. We have to take into account sometimes that the graph's going to go up to a theoretical infinity, but obviously in practice it never will. Okay, and we know the word for this because we talked about it briefly last year, an asymptote, which is when the graph approaches infinity. And so what we say is that this model, or this graph or model of what's going on in the real world, volume, again, fixed volume, radius and length, it's going to approach infinity as the radius drops to 0. So the model falls down when we get to the 0 point, effectively. Again, we're only interested in what happens on the positive side, so we could shift it over. So you can see that we have this sort of shape when we're looking at versus L.